Namaste. Okay. Hey guys. All right. Here's what we're going to do right now. We're going to talk about how to find how fast an object is going at any point in time using energy, and also if you do the reverse, if you throw an object up, how high will it go? Now you did similar problems using kinematics, all right? But now we're going to use what are called energy considerations, and I think you're going to find it's actually easier to solve these problems with energy. Okay, so anyway, so let's watch what's going on here. So let's say, all right, so I have a mass, and let's say it's 5 kilograms, and it's on a cliff like this, all right, and the cliff is 100 meters high. And let's say what I want to do is I want to find, okay, so how fast, if I drop it, how fast will it hit the ground with? Not how fast after it hits the ground, that's going to be 0, obviously, all right, but upon impact, what's the impact speed going to be? Watch how I do this, okay? So, using energy, up here, before it starts to move, all its energy is potential energy, okay? Now, if you watch the other video, the reality is it has a total energy up there, which is its potential plus kinetic. So, but since it didn't start moving yet, its kinetic energy, the value for it is 0. So I'm going to skip that step, and I'm just going to say that right there, it's got its potential energy. In order to figure it out, it's mgh. And upon impact, all right, all of that potential energy up there has now changed to kinetic, all right, upon impact. So it's kinetic. So right before it hits the ground, its height is 0, and its energy would be given by 1/2 mv squared. Okay, tracking on that. All right. Now, okay. So what I can say, because energy is neither created nor destroyed, I could say that the energy that it has right there is equal to the energy that it has right there. So I can just set the two things equal to each other. So here I go. Okay. Now notice that the m's go away, as Grandma Golis would say, like so. And what I'm going to do is I'm going to solve for v. I'm going to flip these sides here and take the square root. And there you have it. It's that easy. So if you were to put in numbers, okay, this would be Give myself a little board space there. And I'll let you figure that out. So you just plug in the numbers, and that would be the impact speed, okay? So notice this expression here, like 2gh, square root of 2gh, all right? Here's how we know that we're on to something. Check this out. Because the other way you solved problems like this before, earlier in the fall, and you did it using kinematics, all right? And so watch what's going on here. Okay, so when you did it with kinematics, you probably would have used the third kinematics equation. Okay, if you recall. All right, and when you would apply it to this problem, okay, A would be G, 9.8. X would be the height above the ground, okay? And V naught, if you're just starting off, would be 0, all right? And so you would get, when you take, so you get, and then, and notice that you're getting the exact same expression if you do it with kinematics equations. That's kind of a sign that we're getting it right. Sign from what? I don't know. God. the universe, whatever God you pray to, or the void of nothingness that you'll become if you're an atheist. All right. So whatever. But bottom line is it works. Okay. Now let's do a variation on this problem. And let's say that now, instead of finding the speed all the way, like upon impact when it falls all the way down, what if we want to know how fast it's going halfway up? Okay. Well, first, in order to solve that, before I explain that, let me give you the concept of a potential energy 0 point. Right. Just watch. Potential energy depends on what we call a 0 point. And you're probably saying, Golis, what are you talking about? Well, here's what I'm talking about. Here, the ball has some potential energy, and then at the ground, we say that's the 0 point. That's where it has no potential energy. Okay? But does it really? Okay? You're going to see, let me show you that this potential energy point is, for the most part, arbitrary. All right. Because what if when the ball hit the ground, where we said, oh, there's no potential energy there, what if I suddenly dug a deep hole right next to it? Now, does it have potential energy? Yes. Okay? And what did I do? Well, I moved the 0 point from here when I dug the hole. Now the 0 point's at the bottom of the hole. So now it has potential energy. Really, the only true place where it would have no potential energy would be at the very center of the Earth itself. Okay? They have no potential energy at the center of mass of the Earth. Okay? All right. But so the bottom line is we could take this 0 point and we can move it. So watch what I do. All right? So we say the cliff is 100 meters high, and normally we'd say the 0 point is on the ground. But if I want to know how fast it's going after it has fallen halfway, then what do? What I do is I'll move my 0 point higher. And I will say, I'm going to pretend, it's not really there, but I'm going to pretend that this is the ground. Now just be careful when you do this. Because if you say this is the ground right there, which is fine, you can. But remember, your height now changes. If this is the ground, your height is not 100 meters anymore, it's 50 meters. Okay? So I'm going to write down, instead of H, I'm going to write H prime, little tick mark there. Okay? And I'm going to do the same thing. So instead of, I'll put a prime there, which means that that's going to be 50 meters now and not 100, and that its energy over here is 1/2 mv squared. And then I'm going to do the same thing. I'm going to set this equal to this, and it would be the same exact process that you just went through when you set them equal to each other, and you get V is equal to the square root of 2gh prime. H prime being the height that you want to know how fast it's going at. But be careful what I mean by, when we say the word height, okay? So if you want to know, for example, if you want to know how fast it's going a quarter of the way down, your height would start there. You pretend the ground is there, and your height would be 25 meters, not 75 meters above the ground. You would say that you would pretend that it fell 25 meters, okay? So just be careful when you do that, because that's a pitfall for students. And then I would plug this in. Okay, and put 50 meters there, and so on, and I would calculate the speed that it would be going halfway down. Okay, so hopefully you find that not too bad. I don't think it is. I think it's pretty easy. I'm going to put some practice problems, okay, on Classroom, and we'll see how you guys do. All right. Now let's try the reverse of this. Okay. And I know it's not perfect. We're using an old chalkboard that I had in my room. Or not in my room, I actually had it in my kids' room. My kids used to play with this and all that. But hey, it's working. You know what? We're Americans, And this is a national emergency, so we make do, because that's who we are. America. All right, let's do the reverse. Okay, so let's shoot something up. So let's say that we have some mass, and we're gonna a ball, cannonball, whatever, and we're gonna throw it up, and we want to know how high it's going to go. Well, we do roughly the same thing. So let's say it goes up with some speed v naught, and we want to know the height that it climbs up to. Okay, so let's use energy considerations. And again, I think you'll find this easier to do with energy than you would find with a kinematics equations. I don't know why I'm blanking on that. Okay, its speed at the top would be 0. Okay, so kind of be in reverse here. So down at the bottom here, its energy is all kinetic. Because let's say it's starting from the ground. All right, and put our 0 point right there. All right, and at the top, its energy is all kinetic, or potential. And again, I'm going to set the two equal to each other. The m's go away, which is kind of nice, and I'll just solve for the height. So h is equal to okay, all I did was take the 1/2 and I put the 2 down there, so don't let that confuse you. And then I would just plug in, that's my initial speed, all right, whatever, okay, whatever that initial speed was, and 2 and then 9.8. And that would allow me to find the speed that, or the height that it would go up to, okay, if it were thrown up at that initial speed. Good to go on that? Okay, now let's say that I wanted to know the speed that it has halfway up. Okay, so watch how I do this, all right? Okay, so what I could do, all right, so let's say I know, let's say I want to find this, the speed that it has, let's say, let's 10 meters up or something like that. Actually, let me just kind of set it up for you, all right? I won't want to get too much into the numbers, but let me just show you how we could solve a problem like this. All right, what you would consider this, you might have to go into the total energy equation for. Okay, so over here at the bottom, its kinetic, its energy is all kinetic, which is 1/2 mv squared, and you could figure that out. Okay, great. Halfway at any point in between there, okay, its energy is mgh, okay, h being whatever height that you're looking at, because it has some potential now and it has some kinetic. Now I'm going to put a little prime there because that speed is different than that speed. And at that point, what you could do is you could set the two things equal to each other. I'm going to get kind of low here, so 1/2 mv squared, that's its initial speed, is equal to, oh, I put an m in there. Sorry about that. 1/2. Okay, and notice m, again the m's go. And what I could do is I could solve for that v prime, all right, because I know it. So just to clean this up a little bit. Okay, and I don't want to make the video too long, but if I knew that initial speed, that's the speed down there, and this is the height that I'm looking at, so I want to know how fast it's going, 10 meters up, so I would put in 10 meters there, and I could solve for that speed right there. Okay? Okay, guys. All right, I think that's enough for now. That's enough to get you guys started, and we'll see how you guys do. Good luck. God bless America, and have a fun apocalypse. It's important to enjoy yourself.